Hello and welcome back. This is Systems Design 522, Fundamentals of Artificial Intelligence, taught at the University of Waterloo in the fall of 2023. And this is Lecture 7 and Backpropagation. So, what are we getting into? Alright, so stories so far in this course. We've been very focused on supervised learning. We're going to continue to be on supervised learning in this lecture as well. We've looked at a bunch of different techniques. We've looked at perceptrons, where we sort of have these features that are defined, and then we do some sort of learning rule that figures out how to weight these features. We have regression, which said, hey, all right, we can go ahead and we have a bunch of features, and then we, instead of doing a learning rule, we invert a matrix, and that tells us our weights. We saw the linear SVM, which optimizes slightly different problem. Instead of just trying to classify correctly or minimize the error in the output, it was also trying to maximize the distance between the sample points and the dividing line. And we showed that there's all sorts of ways that you can do this. You can compute that relatively efficiently. And then we went on and expanded that out to this weird kernel trick thing, which let us sort of effectively use an infinite number of features. And once you've got an infinite number of features, of course, you can learn anything. And now we've got to go ahead and optimize it in different ways and say, okay, well, fine, maybe we're going to end up overfitting to the training data. We need to have some sort of trade-off between being accurate and generalizing to new data. All right. So we have different ways of using these features. We have this way of, we either define our features ourselves, or we go ahead and use this weird infinite space of features. And we also have this other tension of sometimes we're doing some sort of optimization problem to find these weights. And sometimes we are using an online iterative learning rule that is sort of adjusting the weights to sort of gradually improve them. It's somewhat interesting to sort of stop and sort of think, okay, well, of those options, if you can, do some sort of adaptive learning rule that is sort of on the fly, changing the weights and improving systems and making them better and better, there's something that feels really intelligent about that, or at least some people have that intuition, that when you've got the system that is sort of adapting itself on the fly and sort of adjusting the weights in order to improve its job on the task, that seems a lot like what we would associate with intelligence, or at least if we wanted a system that was intelligent, that seems like a feature it should have. That said, it's also this weird situation where you're like, well, hold on a second. If there is an optimal answer and you can just find it by inverting a matrix, why don't you just do that rather than this adaptive adjusting weights thing? Because, clearly, if you could just jump to the right answer, that's more intelligent than doing some sort of iterative, gradual, slow learning thing. So that becomes an interesting tension about what we mean by the word intelligence. Mostly, if we're out of all that, I just want to highlight that both of those sorts of techniques exist. I find that if you're in a domain that's simple enough where you can just solve for the right answer, then just do that. But yes, when we're in situations where there is no mathematical approach of sort of jumping to the right answer, then we've got to use these iterative learning rule things. Fine. So what? Throughout all of that, we keep coming back to the idea that features matter. And people have wanted to learn features for a long time. So none of the stuff that we showed back here, no one was ever learning features. We were always either, we have a set of features that we were given, or we decide, oh, I'm going to use, the polynomials as my features, or I'm going to randomly generate some features, or I'm going to use this weird kernel trick that sort of gives me this particular set of an infinite number of features. So we're picking them. In none of those cases are we actually learning features. And people have wanted to learn features for a really long time. Indeed, sort of like the challenge of trying to learn features is one of the things that the perceptrons book back in 1969 spent a fair bit of time on. It's mostly focusing on looking at the learning rule of the perceptron itself, and sort of near the end of the book, there's this interesting statement from Minsky and Papert. This is arguably one of the statements that sort of caused neural networks to just sort of be abandoned for about a decade. But the quote is, okay, so the perceptron has shown itself worthy of study, despite and even because of its severe limitations. So those severe limitations being, hey, I only have a learning rule on the output, but it can still do lots of cool things. So it has many features that attract attention. Its linearity, its intriguing learning theorem. This is the learning theorem that says, hey, look, you are going to find a correct answer if you use this learning rule, and it'll happen in a reasonable amount of time. And it also has this this fact that it has this clear simplicity as kind of a parallel computation. So just this idea of, hey, look, I have a bunch of features, I'm doing some weighted sum of them. So there's all this excitement about the perceptron itself. And then Minsky and Papert go on to say, but there is no reason to suppose that any of these virtues carry over to the many-layered version of the perceptron. Nevertheless, we, Minsky and Papert, consider it an important research problem to elucidate or reject our intuitive judgment that the extension is sterile. Perhaps some powerful convergence theorem will be discovered, or some profound reason for the failure to produce an interesting learning theorem for the multi-layered machine will be found. So they're saying they're incredibly skeptical about having a multi-layered perceptron. We'll talk about what that means in a moment. But they have this strong intuition that, hey, all of the cool features of the perceptron, those only exist because of it's only working on one layer. And that if you try to extend it to multiple layers, it's going to lose all of its nice features that people liked about it. And that was their intuition, and they showed a few examples in this book. That was apparently a very convincing argument because, people did not pursue this particular direction of research for a while. Of course, that's exactly what we're going to do in this lecture, is we're going to talk about, all right, what do we mean by this multi-layer perceptron? Okay, so as a reminder, going all the way back to the first lecture, what was happening in a perceptron is you had a bunch of features. You had a bunch of input data. You would somehow turn those into a bunch of features. And then from those features, you would just do a weighted sum of those features to produce your output. The idea behind a multi-layer perceptron is say, all right, well, this whole weighted sum thing that we're doing in order to produce an output, can we just also do a weighted sum in order to combine our inputs to create features? So we're going to do a sort of a perceptron, just a single layer of weights. So normally the perceptron would be this side over here. Hey, I've got I've got some input data, x1, x2. I'm going to turn them into features, y1 and y2, and then I'm going to do a weighted sum of y1 and y2 in order to get my output. And the idea behind the multi-layer perceptron is say, hey, let's do exactly the same trick over here. I have two inputs. I'm going to do a weighted sum of those inputs. That's going to create my new feature. Almost. It's not quite this simple. Let's point out why it can't be quite this simple. So if that's all that was happening in this network, there's a slight problem here. So if we were going to say that these y's are just created by doing a sum of xi's with some weights, we're not saying where we get these weights yet. Okay, we'll just imagine we've got these weights from somewhere. We're still going to, we could probably use the normal perceptron learning rule for this side, but what are we going to do over there is a separate question. But let's just imagine we have some weights. If that's what we have in order to produce these features, and then we do the normal sort of, all right, weighted sum in order to produce that feature, well, there's a slight problem here. And that problem is, well, I could rewrite this as y, this vector y is sort of this vector x multiplied by a weight matrix. And I could write this one as this vector z is some weight matrix times y, so it's this one. But if all that's happening is we're doing a weight matrix and then another weight matrix, shoot, that means Z, if Z is some matrix V times Y, and Y is some matrix W times X, then Z is this, and that just means that I could like just multiply those two weight matrices together, and this is just saying that, oh, Z, I can make a new set of weights that just go directly from X to Z, bypassing Y. And if that's possible, then that means that this extra layer is not doing anything. All right, I'm still going to be limited. We'd already said early on that if we just have one layer of weights, then now Z can only be sort of linear transformations of X. There's all sorts of things we won't be able to do. It'll have to be a linear classifier. If this is all that we're doing is just just making features by multiplying by weights, that's not enough to give us more power. That's what that's saying, is that even if I had 10 layers of weights in here, I could just as easily collapse it all down to be just one layer of weights that go directly from X to Z. And so that's not going to give us any advantages. It's still going to be as powerful as a simple perceptron with no features. Okay, so we can't just do multiply by weights. Instead, what we're going to do is we're going to add a little bit of an operation at these 2 points here. We're going to say, all right, we're going to do some weighted sum. We're still going to do this weighted sum, but then we're going to apply some function here in order to create this feature. And we'll talk about different functions, I think, in the next lecture. But we'll apply some function there that will create our feature, and then we'll continue this process. Okay. Technically, we only have to do that in this middle layer, and sort of by tradition, people tend to do it at every layer anyway. So, okay, Z is also some function that we apply, so we do this weighted sum, and then we apply some function. In the original perceptron, that function would be the function is the value greater or less than theta, than that bias parameter. But it can be, we'll talk about all sorts of different functions in the next lecture. But it's just, for now, it's just some function. And it's also kind of tradition also to do a function on the input. You can think of that as like a normalizing or just some sort of transformation of my data just to sort of get it into some nice range. But again, the only one that's necessary sort of mathematically is I definitely need to have something in this middle layer. Otherwise, I could just collapse these two weights. I just multiply these weights by these weights and just directly gets weights that'll go from X to Z, and I wouldn't need this Y. Okay, so that's sort of our core idea. And then we can go ahead and expand that and generalize it, and we can say, hey, all right, well, we could have many layers, right? And then what that would mean is that we're getting things like, okay, at this layer, we're building features. So the features that we're building in this layer are some features of X. And then we're going to build features out of those features. And then we could build features out of those features of features, and then maybe we can go ahead and produce our output. Okay? So this is what this should do, is this should allow us to have much more complex features. And we should be able to arbitrarily complex features. And at any given point, the particular features are going to be, you take the features of the previous layer, do some weighted sum of them, apply some function, that gives you your new features. So we're getting sort of a very regular pattern of how to make new features rather than just saying, oh, it's anything. Here's sort of a regular pattern we can follow. Okay, so that's the idea behind the multi-layer perceptron. And again, back in the perceptron days, people were definitely playing with these sorts of things. But there was this general problem of where do you get the weights, and people would sort of generally hand design the weights rather than have any sort of learning rule because they didn't have a good learning rule for these weights. So let's go ahead and build such a learning rule. All right. So let's start with the simplest case. Let's just pare everything down. So here's sort of, just even how do we generate learning rules is sort of where it started. So let's build a learning rule for like the simplest possible case. So here's a case where I just have two inputs and I'm just doing a weighted sum of those two inputs to produce an output. No nonlinearity, this is about as simple as you can get. And this is simple enough that I don't even have to write it in summing notation. I can actually just write out what y is. So y is just x1 times weight 1, x2 times weight 2, that's y. And what we're saying is, hey, if I have some training data some training data saying, given this X input, here's the Y output that I want. And I wanted to find some way of learning these weights. What could I do? Well, the general process, or one general process for defining weights is to say, all right, or defining some sort of learning rule, is to say, okay, look, if there's some sort of way of writing down what my error is, right? So if I have some target value, if I know what Y is supposed to be, and I know what Y is, I can define my error to be the difference between those two things. And then I can try to minimize that error, right? And so often we would sort of write it this way. So we want to minimize, we want that error to be close to 0. So we write it this way. We write, okay, fine, I don't want the error to be minus 1,000. I want the error to be 0. So that will, this error will be minimum. So if Y is my actual output, T is my target output, and then I square it, so there's always a positive number. Then I do the 1/2 thing out front, just because I know I'm going to be taking a derivative in a moment, and so I may as well put the 1/2 out front. It doesn't change where it doesn't change the weight value that gives me the smallest error. It's just going to make the math a little prettier on the next line. What do I mean by that? Well, look, one way of defining any error rule is to take your error function, take its derivative, and that with respect to the weights, and that will tell you which way to modify the weights in order to reduce the error. Right? That's what the derivative of the error with respect to the weights is. It's how does the error change when you change the weights. All right. So I can take this error, so this Y thing, that's just that. So I can just substitute that in. So Y is this. Now I can take the derivative of this. So if I want to have a learning rule for how should I adjust weight 1, then I can take the derivative of the error with respect to weight 1, and that'll say, okay, if I changed weight 1, how would that change my error? All right, so how do I take the derivative of some nasty thing? Well, okay, this is a polynomial, so the derivative of that is I take this 2, I pull this down, it cancels out with the 1/2, so that goes away, and the exponent reduces by 1, so now I have this big giant thing to the power 1. And then I multiply that by the derivative of what's inside the parentheses with respect to the variable. And so the derivative of this whole big thing here is derivative of that with respect to W1 is x1. Derivative of that with respect to W1 is 0. Derivative of that with respect to W1 is 0. So this x1 is the derivative of this thing here with respect to W1. So that's the derivative of my error with respect to W1. Okay. So I can also sort of do a little bit more, I can substitute back in this thing here. So I can also say, all right, so the derivative of, so how will my error change as W1 changes? And that will tell me how it'll change. And so if I want to reduce my error, then I want to make sort of a small change in W1 in the direction that will make that error become smaller. And so this is one way to define a learning rule. I'm going to say, all right, the amount of change I'm going to make to W1 is going to be negative because I want to change W1 in order to reduce the error. I don't want to change W1 in order to increase the error. So I need to put a minus sign. I'm going to put an alpha. This is just going to be a small learning rate that's just going to say, how much should I adjust my weight by? Probably just make a small change. Multiplied by this. Okay, because this is the derivative of the error with respect to W1. Okay, so that's telling me, as I change W1, how will the error change? I would really like to reduce the error, so I put a minus sign in and I make a small step. So that's going to be one possible learning rule for changing this weight 1. And I can do, I can do a little bit of rearranging here. Pull this minus sign in. I can put it there. Fine. And I can do the same thing. I can derive the same thing for weight 2. So those are learning rules that would adjust W1 given some training data. Hopefully, those are also somewhat familiar learning rules. that is the learning rule that we sort of just intuitively made up for the perceptrons. Right? That is the same learning rule that we were using. Take the error, multiply by the activity, by the magnitude of that input. So what we've got here now is sort of a derivation of where where we could sort of create that learning rule from, sort of in a principled manner, rather than just sort of intuiting such a learning rule. Cool. Okay, this sort of gives us a general methodology that hopefully we can use for more complicated cases. As an example, all right, so what happens if we go through this same process now, but in a slightly more complicated case where, say, this thing here, instead of just being the weighted sum, we're also applying some function. On the previous slide, I used f for the function. Here I'm using g for the function. Both are kind of common, so yeah, you will see both of them. But it's just some arbitrary function. We're going to have to put in that sort of, I did the argument a few slides ago that, hey, we're going to have to put in some arbitrary function in the middle of these features. So we need to be able to figure out how our learning rule changes once we put in these functions. So let's go through exactly the same process, but with this slightly more complicated function for y. Okay, so the error is that. We're still going to take the derivative, or, well, we can do the substitution in. Fine, this is now substituted in there. We're still going to take the derivative of all of this with respect to w1. Now it's just, it's horrible, but the same trick is going to happen. This 2 is going to come down. There's going to be some canceling. This thing in the parentheses is going to stay there. Chain rule is going to say, oh, shoot, we also need now the derivative of this function. So that sort of new term, that term is now going to appear that didn't before. And then we still got that x1 at the end because that's the derivative of the thing inside the parentheses with respect to weight 1. So we get this new term. Again, we can just substitute back in and just to sort of write it in a little bit more compact way. And again, this is the new term that appears. And it's the derivative of that function at a, where a is whatever this input is right now. Fine. And then we can write out our learning rule yet again. Fine. And we can again have these same two learning rules. Same learning rule as before. We just get this extra scaling factor based on the derivative of the function that we end up having at this feature. But it doesn't deeply change our learning rule much. We just find, okay, there's another scaling factor we've got to toss in there. Okay. What about the multi-layer case? Now I've got this twice. Well, let's just write it all out. So these y's are going to be some weighted sums of these inputs. These z's are going to be some weighted sums of these inputs, and in both cases there's this extra function happening here. We're going to do the same trick. All right. If we want, so one nice thing is for these weights here, we've already derived the learning rule for this, right? For these ones here, changing these weights, that just depends on these activities. Okay. Well, that's just the same as this case here, right? It's just we've got our previous layer instead of x here. Okay, but the shape of the learning rule is going to be the same because this here is the same as this last chunk of this neural network. So for the output weights, fine, we can just use what we've already derived. We know the learning rule for this. The challenge is, and the thing that in the perceptrons book, they're like, what the heck, how are you ever going to do this, is how do we get a learning rule for these weights? Fine. Well, let's just go do the same freaking approach that we did for the other cases. It's just, oh, this math is going to get ugly. I want to take the derivative of this error, the error between my actual output and my target output, with respect to these weights all the way back here. And of course, this is just going to end up being chain rule over and over and over again. So the chain rule says, all right, the derivative of the error with respect to the weights is the derivative of error with respect to y. Fine, that's something, you know, we've already been able, that's a little bit easier to calculate. Multiply the derivative of y with respect to these weights. Go ahead and do this substitution, go do this canceling, go do everything, working it all out. It's just cancel it. Yeah, we're just following chain rule over and over and over again. And you can write out the derivative of that error with respect to these weights. It's output times the scaling factor times these weights times these scaling factor times. So we just get more and more and more terms the farther back we go. Okay, but conceptually, it is just using that same chain rule iteration over and over again. And we get a learning rule for these weights. Oh, well, now we have a learning rule for these weights. That seems really nice. Okay. Not only do we get a learning rule for these weights, but the learning rule has a really neat form. Okay. So if we take a look at what the learning rule is for this set of weights, scaling factor times the error at the output times this derivative of this activity times yj, which is this value. Okay. But you'll not, and then the derivative, or the learning rule for this part has a lot of the same terms in it. Okay. And so one way you can see what's happening here is that if I'm doing this sort of learning of these weights, I can take the error signal that I'm already using to adjust these weights, right? It's the same values. And I just, in order to adjust these weights, I need to take my learning up here, multiply it by these weights, and pass it back here, right? So we're taking the error from a later part of the network, and we are using that same error value, and we're passing it back to earlier parts of the network. Right? That's just what this, if you follow through what chain rule says, and when you go ahead and build up this error rule, that's just the form that you get. This is why this particular learning rule is called the backpropagation of error. Okay? It's the recognition that when you do this derivative trick and try to use it in order to figure out which way to adjust these weights, you end up with math that is of this really nice form where I can take the error from later parts of the network and give them to earlier parts of the network. Okay? So the fact that we are propagating that error backwards through the network is why we call this the backpropagation of error learning rule. Cool. All right. So we now have a learning rule that should work for multi-layer perceptrons. And this is the learning rule that's sort of at the foundation of pretty much all of modern AI. And because it's such a foundational learning rule, it's worth taking a little bit of a moment to talk a little bit about its history. I mean, to a certain degree, it is just, it's just chain rule. Like, really, it's just, oh, yes, once you've got this idea of, hey, I want to minimize error, I can do that by taking, you know, whatever it is that I want to adjust about something, I can take the derivative with respect to that, and that'll tell me which way to adjust it in order to minimize the error. All right? So it's just chain rule applied to an error. So technically you could say, I don't know, Leibniz discovered this. It's not quite just that. So the argument is that really backprop is requires two things. One is, yes, we're defining an error function and taking its derivative in order to define a learning rule, but it's also noticing that you can do it really efficiently by taking the error calculation you're using in later parts of the network and passing them back to earlier parts of the network. So having that extra trick makes it much, much more efficient to implement, rather than separately computing the derivative for every single point in the network. So people say, all right, fine. It wasn't, Leibniz didn't come up with this. If we look around for other sorts of sources, there is a, there's a, a nice paper, this theory of adaptive pattern classifiers from '67. which is even before the perceptrons book, pointing out, hey, look, you can do this. You can take this derivative. They're training neural network weights by taking the derivative. Problem is they're not noticing this efficient shortcut that sort of makes it a general purpose, sort of just this backpropagation of error. So it's generally considered this is not an example of, this is not where it was invented. So they don't, they're not doing it efficiently. In 1970, there's another paper, or a master's thesis, representation of cumulative rounding error of an algorithm as a Taylor expansion of local rounding errors. Fine, okay. It does not mention neural networks, but it does have the efficient version of doing this derivative trick. So, some people, anyway, these are definitely precursors to this algorithm. Neither of them are really taking it all the way. If we want something that actually does combine these things, there is a PhD thesis from 1974 that sort of lays this out. It discusses applying it to neural networks, but it doesn't until 82. Again, but it is very definitely looking a lot like neural networks. And the math ends up looking, like it's the same math that we just talked about there, and applies it in lots of weird situations, and even explicitly compares this to brains. So this might be considered the first publication of this algorithm. Other arguments for where it comes from: there's a tech report from '85. There's also a conference proceedings, also from 85, from Jan LeCun, who's still sort of a big luminary in neural networks. So those can also be seen as initial sources, where, again, same learning rule, same nifty approach to creating features, and even sort of applying it to tasks like digit recognition. So here's some of the training data where the input was these images and the output is a one-hot classification. So, good early on. That said, none of these, so you could sort of argue that those might be places where it came from. The paper that really sort of suddenly makes a splash and is sort of the thing that is now cited as this is the paper that invents backpropagation, or at very least popularizes backpropagation, is this 1986 paper, Rumelhart, Hinton, and Williams. Jeff Hinton, of course, still being a rather big luminary in artificial intelligence. But there's actually, of course, just to complicate things, there's two papers that might be referred to with Rumelhart, Hinton, and Williams, 1986. The short one is this Nature paper, Learning Representations by Backpropagating Errors. So sort of explicitly laying out, this is how we can learn representations, learn features, by backpropagating errors. But then there's also, in the same year, there is a chapter in sort of in a book that is bringing together a lot of these parallel approaches, or a lot of these approaches that are based on things that look like neural networks, called Learning Internal Representations by Error Propagation. So both of those come out the same year and basically are the things that sort of make a big splash and people go, oh, okay, I can use this technique for lots and lots and lots of different situations. The 86 paper does indicate both Parker and LeCun as independent discoverers. So that's good. The other stuff, the other earlier ones here, people only found that stuff later. They certainly weren't as widely popular or as widely known. I'll also say that this particular paper gives a really concise sort of description of this process, and specifically puts it in the context of neural networks, and specifically puts it in the context of dealing with all of the problems that perceptrons were having. And so explicitly saying, hey, this big problem that Minsky and Papert had pointed out with perceptrons and said, hey, this nice learning rule that you've got works great when there's only like one layer of weights. how are you going to generalize this to multiple layers? They are explicitly pointing out that, all right, this backpropagation learning rule fixes this problem. And the quote they say is, although our learning results do not guarantee that we can find solutions for all solvable problems, our analyses and results have shown that as a practical matter, the error propagation scheme leads solutions in virtually every case. In short, we believe that we have answered Minsky and Papert's challenge, the one listed over here, and have found a learning result sufficiently powerful to demonstrate that their pessimism about learning in multi-layer machines was misplaced. Okay, so this is a fairly radical change and a big, a controversial fix, or not controversial, but pointing out that this fixed a problem, sort of reinvigorated a lot of interest in neural networks after this sort of pause from 1969 to 86. All right. I think it's also interesting to spend a little bit of time looking at what are the examples that they tried to apply this to, because it's sort of, okay, I can learn features. What sorts of features were they even interested in? Like, what do we mean by these? What are these features? Because even right at this early stage, right in these early papers, they're interested in pretty complicated. They're interested in features that sort of maybe say something about human cognition. If these are supposed to be learning rules that teach us about cognition, that teach us about complex, intelligent things, can they learn the sorts of features that we might expect people to learn? And what do we sort of mean by that? How would we even test that? So one of the tasks that they emphasize in this, or that they use in this very first paper to show that we can learn pretty weird features using this particular learning rule, is they actually try to train up a family tree, or two family trees. So this is what I'm showing here on the page. Is this is the training data that they're going to use to feed into the network, and then to try to be able to test whether or not it's able to do this task. And what is this training data? This training data is saying this is a family tree. And this is saying things like Alfonso and Sophia have parents, and those parents are Lucia and Marco. Okay? And then Marco's parents are Piero and Francesca. Or Arthur's parents are Christopher and Penelope. Okay? And then other things like, for instance, Charlotte's grandparents are Christopher and Penelope and Andrew and Christine, and so on and so, and aunts and uncles and all sorts of other different relationships in here. So this is just a way of depicting that training data. Of course, in order to turn it into data to train up a neural network, I've got to turn that into vectors and numbers. And this is the sort of diagram that we're going to use to sort of depict this network. Depict how we're going to shove this into the network. So what the heck is this diagram over here? Okay, so this is our neural network. The bottom is the input, and I've got one big block of input over here that's going to be which person I'm talking about. And then I've got another block over here that's indicating what sort of relationship I'm talking about. Parent, cousin, niece, nephew. All right. For each of these squares, so you can sort of imagine a bunch of squares in here. That's just a big giant vector, most of which are set to 0, one of which is set to a 1. Okay, and the one that's set to a 1 is drawn with a big white square. Okay, so this is a one-hot encoding of a particular name, a particular person. And then over here we have a one-hot encoding of a particular relationship. So I guess there's like 12 different relationships, and we're saying one of them in particular. So our input is going to be mostly all zeros, and there's going to be 2 values that are set to 1s. Okay, there's going to be a 1 for the person and a 1 for what relationship it is. That's going to be my input to the network. I'm then going to have a set of features of 6 features that are built up out of those, and another 6 features that are built up out of these. And then I'm going to have 12 features. Those features are going to be built up out of these 6 and these 6. Then I'm going to have another 6 features that are built up out of these 12 features. and then I'm going to have an output. And this output is going to be a separate square for each person. And the numerical value, there's going to be some values that are large, some values that are small. We're going to, when we run the network, each output is going to have some value. And we're going to just, instead of writing out the number in these things, we're just going to draw it with these sorts of squares of different sizes. So the squares of different sizes tricks sort of was a popular way of depicting, instead of writing out a bunch of numbers, 0.1, 0.1, 0.1, 0, 0.5, 0.1, instead of just writing out a bunch of numbers, they draw it with these squares just to make it a little easier to visualize. They're also using that same trick in these intermediate layers. The size of the square is the magnitude of that feature for this particular input. So what this is saying is to say, all right, I have an input indicating Colin, and we're asking whose Colin's aunt is. Then I've got two of these values that outputs that end up being very large, and Colin's aunts are Margaret and Jennifer. So given these trees, you could build up a bunch of training data. You could leave a couple of those training points out because you don't want to test on your training data. So they trained up on a whole bunch of these relationships. They left out a couple of relationships, including this one. And then you can see, does the network generalize to understanding, oh, yes, I can predict who Colin's aunts are. Okay. So that sort of was one of their core examples of, all right, it is learning feature, whatever the heck this thing is learning, it is learning sort of something about these structured relationships. Okay. So whatever the heck these features are inside here, somehow that's encoding information that's allowing it to pick up on these sorts of regularities about these family trees. Cool. What other things do they try? So in the in these various papers, they showed a whole bunch of different things. Other fun examples. Here's one where the input pattern and the output pattern are identical. So that seems like that should be a really easy pattern for it to learn. But then what they did is they sort of were sneaky and they said, hey, all right, try doing that, but with a small number of features. Okay. And what this should do is this should force it now. It's got to figure out some sort of interesting features. So for instance, if I've got 8 inputs and each input is a 1 followed by a bunch of zeros, or a single 1 in each of these cases, I need to have the output match the input. Somehow these features here need to be an efficient representation of this input data. Okay, so if we put in a little bottleneck here, if we say, hey, I'm only going to use 3 features, how am I going to represent this, these 8 different input patterns? Well, again, if I was a person coming into that task and saying, oh, I have 8 values, I need to encode that using 3 feature values, well, that's binary representation, right? I could just go ahead and build features that are binary representation. And then the question, of course, is, does the system learn those features? And the answer is yes. Yes, it does. So it goes ahead and learns this pattern. It learns exactly those features. Sometimes, it doesn't have to learn exactly those features. In this particular case, sometimes it'll, like nothing's forcing it to use binary in here. It might say, oh, okay, I can encode information using -1s, 0s, and +1s. But one of the things that it is quite capable of learning and often does is, oh, okay, it'll just use binary representation here to represent the 8 values. Okay. What we're pointing out there is these are the sorts of features that these systems can learn. Of course, XOR, we can go ahead and learn. Everyone always wants to test on XOR just because we know it's a nonlinear problem. And indeed, you can go ahead and sort of generalize XOR in terms of, fine, instead of just having 2 inputs, you could have like 4 inputs, and it can go ahead and learn that fine. It can also go ahead and learn 2-bit binary addition. So again, these are all things where you can just generate a bunch of training data, train up the network, and see what it goes and learns. In this particular case, they had a lot of fun sort of playing around with, well, what structure do I need in the network to do this? Especially since binary addition, there's sort of a known hand-designed network that could do it. And so they could sort of play around with, all right, well, what if we give it that same structure, And can it learn the weights? And the answer, of course, is yes. But the one thing that's being highlighted here is this backpropagation algorithm doesn't require you to have layer and layer and layer and layer and layer. You can also sort of bypass steps. You can organize this network however you feel like. It's just you've got to be a little bit careful when you go ahead and compute the error backpropagation learning that you've actually got the math all correct. But it's always that same structured math in any case, no matter what the structure of this network looks like. That said, it's sort of really, really common to have sort of these all-to-all layer networks. And then finally, one of the other things they ended up doing is can we recognize images? And in particular, they were doing this task here where your input is a big square grid of mostly zeros and then some ones following that define some sort of shaped pattern. And that shape is either a T or a C. And then the question is, can the networks learn to classify between a C and a T? And here they actually even started structuring the network even differently, such that this feature only grabs data from, or is only sensitive to a particular set of the inputs. So we have some sort of structure there. Again, we can still apply backprop and it all works. So there's a whole collection of these interesting basic tasks that were shown, basically just sort of showing this wide variety of things, wide variety of features can be learned using this one consistent error propagation rule, and all you need to do is sort of restructure your network to do wildly different things. It'll still learn good weights. Okay, all of that. What the heck was that? So that gives sort of a whirlwind overview of backprop. The core idea about everything we were just saying here is, hey, we're going to build up features, and we're going to build features by doing weighted sums of our inputs, and then apply some nonlinearity. And then we can build features out of those features, and then we can build features out of those features, et cetera, et cetera, et cetera, and make more and more and more and more complex features. In order to find the weights that create those features, we're going to do this standard trick of we've got an error function that just simply says, hey, I want my output to be as close as possible to my desired output. I'm going to take the derivative of that. I'm going to use the derivative of that with respect to the weights to figure out a learning rule that tells me how to adjust the weights. And we're pointing out that this derivative has this really nice form, just because of how chain rule works, that all the math that we do for things later in the network, I can take that same math and pass the information backwards to earlier stages of the network, so that I don't have to recompute it all the time. So that the error at the later stages can be backpropagated to the earlier stages to help compute that error. That makes it a nice, reasonably efficient learning rule to do. So this ends up giving us a nice general approach to do supervised learning. There's no guarantee of success. So there isn't a nice proof that says, hey, this will always work. But it seems to just work reasonably well as long as you have enough features and enough layers. And people have, right from the very beginning when this was created, we're applying this to sort of cognitive type tasks that we're trying to sort of start modeling the sorts of reasoning that maybe people might do. And it should automatically find relatively good features. All of that being said, those initial results are sort of painting a fairly rosy picture of things. There's still a lot of hand tweaking and playing around that can seriously affect how well it works. For example, why, when doing this structure, did they end up saying, okay, I'll put 6 here and 6 here and 12 here and 6 here? Why did they pick those numbers? Why not 8? Why not 4? Why not 12? Why not 100? There's a lot of hand tweaking and designing sort of hanging around inside each of these networks. So it's going to be a little bit tricky to use in practice, and we will see that more in the next lecture. Okay, thank you very much, and we will see you for the next one, which will be backpropagation part 2. Thanks. Bye.